so I'll point to this one. Here is my sampling distribution with this. This is my distribution of sample means when the null hypothesis is true. Like this is the sort of sampling distribution that we've sort of talked through and worked about and stuff like that. So HO is the sampling distribution when the null is true. But here, H1, this is the sampling distribution of the mean if the null hypothesis is false. This is actually what's going on in real life, okay? And the placement of this is entirely dependent on what that mean is, right? If the mean is very much different than what it is in the null, then the distribution is going to be way out here. If it's very close, it starts to go through an overlap, okay? And so if we go through and we take a look at this, in this graph, the heavily shaded area here, these are the values, or this is my alpha level. On my null distribution, this is where my alpha is. These are the values of my test score that are going to tell me that I can reject the null hypothesis, right? And so anything in this light shaded gray area, if I find a test statistic or a result or a mean that's anywhere in here, what is the decision that I'm going to make in terms of reject, fail to reject? On here, what do you think? Yeah, so if I hit, so here's my null, the white one is my null model, right? But that's hypothetical, it's not true, right? My null model determines where my alpha is placed, right? But what I'm actually drawing from is this alternative model, this alternative distribution. This is where I'm actually getting my scores, right? So can I get this? Is this a real value I can get out of my data? Nope, because that's just part of the null distribution. Here, this distribution is all the possible scores that I could get, right? But if I get any score that's in this like light shaded area here, on here, what is my decision? Do I get to reject or fail to reject the null hypothesis? I would fail to reject the null hypothesis, right? Even though these are all values, these are possible values I can get from the actual population. This is what's actually going on, but these are all values that overlap with this null distribution, right? Now, what about on here, anything in sort of in this sort of white end is the upper end of the distribution? What's my decision there? In this top area up here.
You can't reject.
Yeah, I would reject the null hypotheses here because these are all values of this distribution that I can get that are going to go through and sort of exceed that critical value here, okay? But if I'm looking at this with these overlapping distributions, right? If I spot on predict in I get a sample that's the actual truly represents the population mean, in this setup, do I get to reject the null hypotheses? Nope, I don't, right? Even though I've got a perfect sample, I fail to reject because my test doesn't have enough power to claim a difference here, okay? It's only if I get something that's inordinately high that I can go through and reject the null hypothesis, okay? So again, if we go through and we take this same scenario, and let's say here I have a sample of 80, or my null is 80 and my actual population value is 86. So we've got quite a bit of overlap in these distributions, right? Let's go through and change this around a little bit though. Let's increase the difference. My null value is 80, but my actual population value is 90. What I get is more separation. I get more separation in terms of these distributions. So here's my null, my null curve, right? That's just hypothetical, it's not real, right? But it is what the distribution I would expect if the null hypotheses were true. But here's my actual population, or sampling distribution that I'm pulling from. And now all of a sudden here, again, what's happened to the likelihood of me getting a value out of this distribution that prevents me from rejecting the null hypotheses relative to this? Is it gone up or down? Done.
You're only going to like find an effect for it since it went up.
So okay, so my distribution went up, so it increased, right? But what's the likelihood of making a type 2 error?
You're less likely to make a type 2 error or reject the null hypothesis.
Yeah. So my type 2 error goes down here, and so the likelihood of me finding an effect is higher. And here now in this one, because I've got more separation, if I spot on, get the right value, if my sample gets like right on the actual population value, this is a value that's still going to allow me to reject the null hypothesis, right? So again, we can think about power as overlapping distributions, okay? And for clinical folks, if you ever get into clinically significant reliable change, there's sort of, again, same type of thing, is sort of looking at overlapping distributions between what we would say like a normal or healthy sample and a sample who's struggling with psychopathology or things along these lines. Okay. So again, what we're seeing of these two examples, Lexi, which one of these samples represents a larger effect size? Or which one of these scenarios represents a larger effect size? Yeah, this one right here. Right here we have a larger effect size. And so the number of people we need in our sample to achieve adequate power is lower for this one than for this. Here, the null hypothesis is false. My population of interest does not have a mean that's consistent with the null model, but it's not that far off. And so what I'm going to need is a lot of people to go through in order to identify sort of that. Okay. And Jenna, as my sample size increases, right, what happens to the variability of these sampling distributions? What's that? The variability of these. What happens to my standard error as my sample size goes up? It goes, right? And so think about like this situation, right? Let's say this is my distributions with sample size of 50. Right? If I were to jack this up to sample size of 300, these means are still the same, right? But the distribution of those, the variability of those starts to shrink up to the point where these could be non-overlapping just because I've got much more precision in that sampling distribution. All right, this is sort of both of these, I think sometimes you have to just kind of sit with it and look at it a little bit, but once it clicks, it's like, okay, I understand what's happening. People, sort of any questions before we move on about kind of thinking about these? And again, either one of these are completely fine ways if we want to think about this as if, yeah, I were to perform this over and over and over and over again, and how many of these tests would identify an effect and how many wouldn't. Or thinking about things as overlapping distributions, they're both perfectly fine and good ways to go through and think about things, but just kind of a little bit different look at this. All right, cool. So influences on power, my effect size, okay? My effect size is going to reflect the magnitude of the difference between my null value and my actual value that's out there in the population, okay? If I have larger effect sizes, it's going to result in greater power. If I'm trying to find, like, think about this as, like, am I trying to find a penny in a field, or am I trying to find a boulder in the field, right? One of those is going to be much easier to detect, much less effort to go through and identify things, right? So if I'm looking at really big effects, the timing of the resources and stuff like that are going to be smaller. If I'm looking for something that's very subtle, it's going to take more work, I'm going to need more resources, I'm going to have more precision, okay? In general, what's the size of effects that we're looking for in behavioral sciences? They tend to be small, okay? Sometimes you read a power analysis, like, well, assuming a large effect, this is all my sample is adequate. Like, well, I don't know. Like, assuming I have $1 million, there's a lot of things. Like, I don't know, like what's the basis for assuming that your effect size is going to be large outside of wishful thinking, right? So this is where it takes some work to go through, know your literature, and have an accurate estimate of the effect that you're looking for, and then also taking into consideration that just the way our science is built, whatever effect size the estimate we have based on literature is probably too big anyway, and so needing to be very thoughtful in terms of how you're doing things. It's a free country, you can make whatever power estimate you like, but you really got to think about, am I sort of lying to myself and just falling into the wishful thinking fallacy with things? Okay. Alpha level, if I increase my alpha level, it increases my power, right? If I say my alpha level is 0.20, then it makes my power bigger, right? but probably can't get away with that because science won't let you do that, or reviewers won't. Population variance, variability in the distribution of my sample means increases as my population variance increases, right? Because again, my standard error, right? So as that gets bigger, my standard error gets bigger, right? Makes it harder to find my effect. So technically, all of these, my population effect, my alpha level, and my population variance, all impact my power of my test. Can I do anything about these three? Not a ton. I can get a better effect size if I use measures that are more precise. There's less static there. So just having good methodology and having good measurements will improve sort of this attenuation of effect due to improve the attenuation in the estimate of effect if I'm just using good measures, right? There's less static in there. Alpha level, I could change that, but my reviewers aren't going to let me, so I can't really do anything with that there. Can I change the population variance? No. I mean, I can with good measurement. If I sort of just have a perfect measurement and I'm measuring things without error or very little error, I'm going to have less variability than if my measurements are all over the place. So there's some stuff that we can do and build in just good methodology that's going to go through and increase the power of our tests. But the real thing that we do here is change the sample size. The variability of my distribution of sample means decreases as my sample size increases, okay? And again, if we look at our standard error, right, if I jack that, sort of jack that way up, my standard error goes way down, and then what happens, my test statistic goes way up, okay? So this is the thing that we have the most control over. Certainly thinking about good methods and good assessment is important. That's gonna contribute incrementally to my power, so that's always something that's good to do. It also makes my research more credible. But really, the biggest impact that we have on, that we can have on the power of our test is always going to be our sample size. Questions about this? All right. Oh yeah. What do you call the variability of our sampling distribution? When just guess, like on the midterm, if you don't know, if you're like, it's standard error, I guess, or I got it. It's statistically like choosing D on a multiple choice test. I mean, you're probably going to be kind of right maybe in some way. So, all right. What did we use? Yeah, there we go. That's a pretty low hanging fruit there, but whatever. All right. Estimating our effect size. There's some different things we can do here. Best thing that we can do, because we need to have, if we're going to run power estimates, we need to have an estimate of effect size. Best thing that we can do is go through and look at existing research, stuff that's done something similar to try and generate an estimate of the effect that we're likely looking for. So it's really important really highlights why it's important to report means, standard deviations, other relevant statistics in our reports, so that other people can go through. You might not be interested in a specific relation effect or something like that in your data, but someone else might be. And so that's not say you have to anticipate what everybody else might find interesting forevermore into the future, but if you're reporting mean, standard deviations, things like that, people can go back through and take a look and find what that is, right? So again, I've got a study. I got my thesis, I have my dissertation, I have my grant proposal, I want to run a power analysis. First thing I need to do is figure out what effect am I looking at, right? And sort of existing research is going to be our best place for this. Now sometimes I'm going to be doing something that is completely novel. No one has ever done it before, right? There's no research, there's no literature base for me to even start guessing like what this effect size might be. One thing that would be a real boss move to do is start thinking about how large of an effect would I need, right? Thinking about what magnitude effect would I need in order for this, if I were to find an effect, for it to be meaningful, right? So let's say I have developed a skills training course for GRE. GRE is dead. I don't think we're ever coming back to GRE. Shady's like, nah. But let's say that we were sort of back in not too distant history, and I were to say, in order for this to be meaningful, we would need to see a shift of about 40 points on the GRE in order for this to be meaningful, right? What I could do is I would say that if we're assuming a standard deviation on GRE scores of 100, I would need to find an effect size of about 0.4 to make this a viable intervention, right? What I could then do is, I don't know, I have no idea, no one's ever done this before, so who knows what the effect I'm going to get, but in order for this to be useful, I need to have an effect of about 0.4. So what I could do is I could power my test to identify an effect size of 0.4, right? Now, if I fail to find evidence for my test, I don't know if it's necessarily because there's not anything going on there, or my effect size was too small. My effect size is actually 0.2 instead of 0.4, and I didn't have enough people to identify that effect of 0.2. But the idea being, if my effect actually is 0.2, it doesn't matter because it's not a useful thing to do anyway, right? So again, best case scenario, if there's anything to pull from, like if anybody in the universe has ever even looked at the relation or difference between this, you can go through and find things, right? And calculate. Sometimes it requires a little bit of legwork, sort of working backwards from mean, standard deviation, test statistics, things along those lines, combing through appendices or tables or things along those lines. But you you generally get something that at least ballparks here. If you can't, try and think about, like, is there sort of a level that I would need to detect in order to make this credible? Last option is just go through and just kind of guess using our conventional cut points, right? They'd be like, well, I'm expecting this to be a small effect because the stuff that we look at in behavioral sciences is generally small, and so I'm just going to power my test to detect a small effect. Pretty conservative approach to go through and do things, right? And so that would be, I guess, maybe reasonably defensible. Less defensible is when you're going through things, reading things with people like, well, I'm assuming a medium effect size, and so this is the sample I would need to go through and identify a medium effect. Based on what, right? Just like hopes and prayers, right? Like I just kind of wish that I was looking for a medium effect size. Like absent some sort of compelling argument, just like guessing anything, or like, so I've gone through and powered this to detect a large effect. Tell me why you think you're going to yield a large effect. Like, what is the basis for this, right? So here, when there are no other, like this has failed, this is an option. People do this way more, but again, sort of what you need to be able to do is be able to just go through and defend like why you're expecting this. And if there's nothing in the existing research and sort of there's no reason to expect a large effect size, right? Like if you failed here, then this is just wishful thinking, right? So how I liked this, when talking about estimating effect sizes and power, I don't know, often translates into that far ahead. I haven't thought that far ahead. For me, I think it's more like I didn't give it a shot because it sounded complicated, so I just said I'm sort of expecting a medium effect. That seemed like a nice compromise. But if anybody is going through and thinking carefully about it, you've got no reason to go through and do this, particularly if it's an area where there's lots of stuff out there. Right? Like you're telling me that no one in the universe has ever thought to look at, like sometimes when I'm reviewing papers back, the literature has not looked at the association between experiential avoidance and PTSD. That's probably not right. Let me do a quick Google search and find like 50 different papers. So nice try, give it another shot, go back through. I'm not talking about students, I'm talking about actual stuff that comes across your desk as a reviewer, right? So just thinking carefully, and again, this is really emphasizing knowing your literature, knowing what people have done. One, it sort of keeps you from looking ridiculous in front of people, but two, it also is going to help you put your results into context and be able to start talking about practically what this means, how this fits into theory and things along those lines. Okay. All right, let's go through, take a break here, and what we'll do when we get back is we'll start talking about non-centrality parameters.